Welcome to The Prophet in the Cold, Alfred Wegener and the Quest for a Dynamic Earth. In this tidal movement, we step into the frozen frontiers of scientific discovery to follow visionary meteorologist Alfred Wegener. Challenging the static worldviews of his era, Wegener dared to propose that our continents are not fixed in place, but constantly drifting across the globe. Set against an icy canvas of polar field notes and early geological diagrams, this slide introduces his relentless journey to reshape how we view our living, breathing planet. This presentation will concentrate on his contributions to geophysics and atmospheric dynamics. It begins with a remarkably simple observation, one that anyone glancing at a world map might notice. Look closely at the coastlines of South America and Africa. Their mirroring shapes seem to fit together like giant puzzle pieces. While others dismissed this alignment as a mere quirk of nature, a 30-year-old German meteorologist named Alfred Wegener refused to treat it as a coincidence in 1910. This single, compelling visual insight sparked his journey to challenge existing geology and uncover the true dynamic nature of our drifting continents. Wegener was no traditional geologist, he was a true polymath who refused to be confined by rigid academic boundaries. Earning his PhD in astronomy from the University of Berlin, he synthesized diverse disciplines, from planetary motion and atmospheric thermodynamics to geophysics. At the intersection of these fields lay paleoclimatology, the key that unlocked his revolutionary perspective. By stepping outside narrow specialization and viewing the Earth system as an interconnected whole, Wegener saw what others missed, laying the foundation for a sweeping revolution in planetary science. Before grounding his theories in geology, Wegener took to the skies to master atmospheric science. In 1906, alongside his brother Kurt, he set a world endurance record by remaining aloft in a balloon for 52.5 hours. He brought that same relentless empirical discipline to analyzing extreme weather, sifting through centuries of historical reports to define the mechanics of tornadoes and waterspouts across Europe. Whether staying airborne for over 2 days or untangling atmospheric turbulence, Wegener demonstrated that even nature's most chaotic systems yield to careful, dedicated observation. Driven by a relentless quest for empirical data, Wegener traded the laboratory for the brutal reality of the Arctic. Believing polar research was crucial to understanding global atmospheric circulation, he pushed scientific frontiers on the 1906 Denmark expedition by using kites and tethered balloons in polar skies. By 1912, he completed the longest foot crossing of the North Greenland ice cap and achieved the first overwintering on the inland ice. Wegener proved that revealing Earth's deep mechanisms required not just intellect, but extraordinary endurance in the world's most unforgiving environments. On January 6, 1912, Wegener introduced his radical hypothesis, continental drift. He proposed that Earth's landmasses were once united in a single supercontinent, Pangaea, that fragmented and slowly drifted apart over time. To prove it, he mapped continuous bands of evidence across vast oceans, matching geological rock strata, identical fossil distributions of Mesosaurus and the plant Glossopteris, and paleoclimatic markers like glacial striations in tropical regions. These aligning clues challenged conventional science, painting a revolutionary picture of a world once unified and continuously in motion. Here, two opposing visions of Earth collide. The establishment clung to a rigid, static planet, explaining shared fossils with sunken land bridges and mountain ranges through a cooling, shrinking Earth. Wegener countered with a dynamic vision, mobile continents plowing through the ocean floor and building mountains through massive collisions. Unwilling to abandon their immobile crust dogma, the scientific community fiercely mocked Wegener's revolutionary ideas, dismissing them as delirious ravings. While Wegener's evidence for continental drift was overwhelming, his proposed mechanism was fatally flawed. He suggested that centrifugal forces from Earth's rotation, Paulflucht, and tidal attraction drove the massive movement. Physicists swiftly proved these forces were orders of magnitude too weak to displace continents. Wegener found himself in a tragic scientific predicament. He could clearly see the hands moving on the planetary clock, but he could not open the back to reveal the internal gears driving its motion. Wegener was dismissed by mainstream geologists for being an outsider, a meteorologist. Yet this background was his ultimate superpower. Having devoted his career to studying the fluid, constantly shifting thermodynamics of the atmosphere, he alone possessed the perspective to see past the rigid surface. Wegener recognized that over deep time, the solid Earth behaves just like the skies above, driven by mantle convection, thermal plumes, and the very same dynamic principles. In 1930 came the ultimate test. Driven to gather continuous meteorological and glaciological data, Wegener launched an ambitious expedition to establish IceMet, an observation post deep in the center of the Greenland ice cap. Spanning from edge camps across a vast frozen wilderness, the mission soon ran into severe delays and unrelenting weather. As winter rapidly approached, IceMet was left dangerously unsupplied, setting the stage for a desperate and perilous struggle against the Arctic elements. In September 1930, facing impossible odds, Wegener, Fritz Loewy, and Rasmus Wilhelmsen set out into the Greenland interior to save their starving colleagues at IceMet. Plagued by blizzards, frostbite, and failing snowmobiles, the men were forced to rely solely on dog sleds and sheer willpower. As they climbed 3,000 meters across 400 kilometers of frozen wasteland, temperatures plunged toward a lethal -60 degrees Celsius. Turning their rescue effort into a desperate, harrowing trial of human endurance against an unforgiving wilderness. Against all odds, the expedition reached IceMet, successfully delivering critical supplies. On November 1, 1930, Wegener celebrated his 50th birthday surrounded by the endless ice. But the return trek demanded the ultimate sacrifice. Overcome by extreme physical exertion, Wegener suffered a fatal heart attack. He was buried in the ice by Wilhelmsen, who soon after vanished forever into the blinding Arctic whiteout. Entombing a visionary scientist within the frozen wilderness he gave everything to understand. Decades after Wegener's death, the missing gears were finally revealed. In the 1960s, deep-sea exploration and seafloor spreading provided the precise mechanism he lacked. Though Wegener incorrectly believed continents plowed through ocean crust, modern plate tectonics proved his fundamental premise right: Earth is dynamic and in motion. Driven by mantle convection, vast tectonic plates carry both continents and ocean crust together. Validated at last, Wegener's observations of fitting coastlines and matching fossils were fully vindicated, completing the triumphant resurrection of an idea that reshaped planetary science forever. Today, total vindication arrives from orbit. Modern GPS satellites measure the very continental drift Wegener proposed down to the millimeter, tracking plates shifting across the globe at centimeters per year. Though Alfred Wegener died in the freezing cold, mocked by his peers, history has crowned his legacy. Today, he is celebrated as the father of modern geodynamics, the visionary who taught humanity that our Earth is not a static rock, but a living, moving machine. While world-renowned for continental drift, Wegener was equally an atmospheric pioneer who brought rigorous empirical observation to nature's most violent vortexes. Set against historical European mapping grids, this slide introduces his groundbreaking contributions to severe storm dynamics, exploring how he systematically dissected the mechanics of tornadoes to lay the foundational framework for modern severe weather research. World War I fundamentally altered Wegener's trajectory. Mobilized as an infantry officer in August 1914, he saw fierce combat along the Western Front in Belgium. After sustaining severe gunshot wounds to his arm and neck in October, he was declared unfit for active infantry duty. Reassigned by January 1916 as commanding officer of Station 12 in Mulhausen, his routine observation duties offered an unexpected gift: time for independent research. Out of the crucible of war came the vital opportunity Wegener needed to advance his scientific pursuits. In July 1915, while recovering from wartime injuries, Wegener recognized a critical flaw in early meteorology: excessive theoretical speculation. Writing to Vladimir Koppen, he insisted that true scientific progress stems not from abstract theory, but from meticulous empirical observation. Grounding his work firmly in reality, Wegener deliberately turned his focus to tornadoes, a subject then considered out of fashion. where he could rely entirely on hard, observable data to unlock physical truths. In April 1916, Wegener demonstrated the power of citizen science following the Trace meteorite fall. Conducting over 100 interviews with everyday eyewitnesses and sifting through newspaper reports, he plotted scattered testimonies onto a single map to calculate the object's trajectory. His crowdsourcing method yielded a dramatic triumph. In March 1917, the meteorite was discovered near Trace, precisely where his calculations predicted. Wegener proved that ordinary observations, when systematically synthesized, could pinpoint extraordinary discoveries. Prior to 1917, European meteorology was clouded by centuries of speculative myth. Driven by empirical rigor, Wegener systematically dismantled these long-held theories, rejecting Peltier's electrical hypothesis, Rye's thermal surface heating model, and various volcanic or downpour concepts. Instead, he championed the mechanical hypothesis, aligning with roots dating back to Aristotle. Wegener demonstrated that physical rotation is the primary driving force behind tornadoes, which subsequently produces thermodynamic effects and condensation. By casting aside speculative myths in favor of mechanical physics, Wegener anchored severe storm research firmly in empirical science. Written in the field in 1916 and published in 1917 despite wartime paper shortages, Wegener's Wind und Wasserhosen in Europa established the first pan-European severe storm climatology. This exhaustive treatise systematically catalogued tornadoes and waterspouts across the continent. Wegener examined every dimension of these violent systems, from underlying weather conditions and vortex rotation kinematics to damage paths, electrical phenomena, and sensory details like noise and smell. Through this landmark publication, Wegener transformed scattered severe storm reports into a unified, rigorous scientific discipline. Working from a wartime desk in Mulhausen, Wegener set out to tame centuries of chaotic weather observations. He gathered a vast array of historical sources, from ancient chronicles and letters to 19th-century reports, and systematically cross-referenced, verified, and mapped eyewitness accounts. Through this rigorous analytical process, Wegener transformed scattered, unorganized data into a definitive catalog documenting 258 tornadoes and waterspouts across 14 European countries, turning centuries of chaotic observations into structured atmospheric science. From his extensive catalog of 258 historical events, Wegener derived the first definitive behavioral profile of European tornadoes, estimating at least 100 occurrences each year. By plotting seasonal and diurnal cycles, he uncovered striking patterns. Tornado activity surges dramatically during the warm summer months of July and August, while daily occurrences peak in the late afternoon. Through these quantitative charts, Wegener demonstrated that European tornadoes are not chaotic anomalies, but predictable atmospheric phenomena governed by clear seasonal and daily rhythms. By synthesizing European data with U.S. records, Wegener revealed a stark transatlantic contrast in severe storm behavior. Comparing just 35 European tornadoes from 1884 to 1887 against 777 American tornadoes from 1883 to 1886, he highlighted dramatic regional differences. European storms peaked in summer with a low 5% fatality rate, whereas U.S. tornadoes surged in spring with significantly higher mortality. Wegener speculated that ocean placement, east versus west, drove this atmospheric inversion, demonstrating how geography dictates severe storm dynamics across the globe. Wegener's influence extended far beyond his own studies, sparking a brief golden age of severe storm research through mentorship. Meeting meteorologist Johannes Letzmann in Estonia in 1918, Wegener inspired a powerful collaboration. By 1928 in Graz, Austria, Letzmann joined him to explore vortex dynamics and mother vortices. This legacy culminated in 1937 when Letzmann and Harald Koschmieder published the first comprehensive WMO guidelines for investigating tornadic phenomena, permanently anchoring Wegener's methodology within international meteorology. Despite early momentum, European tornado research suffered a tragic collapse. Following Wegener's death in Greenland in 1930 and the devastating disruption of World War II, key researchers like Letzmann lost their academic standing, bringing European storm studies to a near-total halt. Left untranslated, Wegener's 1917 masterpiece faded into obscurity during a long scientific dark age, leading modern meteorologists to incorrectly assume tornadoes were strictly an American phenomenon until the late 1990s. A century later comes ultimate vindication. Modern supercomputers and ESSL data have expanded Wegener's early findings, revealing an average of 242 European tornadoes annually. Yet, despite analyzing data entirely by hand 100 years ago, Wegener's calculated seasonal and diurnal curves match 2016 supercomputer findings flawlessly. Though modern technology vastly expanded the recorded data volume, Wegener's original insight into severe storm behavior proved extraordinarily precise, firmly cementing his legacy as a true pioneer of atmospheric science. In 1916, Wegener created the blueprint for modern severe weather tracking by crowdsourcing letters and newspaper clippings from everyday observers. Today, the European Severe Storms Database relies on this exact same methodology to collect public eyewitness reports. Wegener's most enduring legacy remains his validation of the citizen scientist, proving that careful, empirical observation outlasts theoretical speculation, forging a timeless model that continues to power atmospheric discovery today. Alfred Wegener stands as a true pioneer of both earth and sky. He recognized that the very same meticulous empirical observation needed to trace drifting continents beneath our feet could decode the violent storms swirling in the atmosphere above. His landmark 1917 climatology remains an enduring testament to the power of dedicated observation, proving that rigorous science can unlock the dynamic mechanics of our entire living planet.